Okay, hi. So we'll continue our discussion of the Fourier transform, and this is in continuation with the lecture I have already uploaded. So let's just relook at what we just did in that lecture. Why did we? Okay, I'm sorry. Let me take the point. Yeah, okay. Why did we want the Fourier transform? Okay, the question was, why did we want the Fourier transform? We had the Fourier series. So the thing was, Fourier series was only for periodic signals, okay, but this is for the series was only for periodic signals, but all practical signals are aperiodic, right? Any signal which you see is actually a aperiodic signal, a practical signal, because it has to begin at some point. I mean, it does not, nothing exists from minus infinity to plus infinity. Even if I mean, like physical signal has to be generated by some physical equipment, and that physical equipment has to be powered. So only when the power is turned on does that signal begin to exist. Even if the power never goes off and the power keeps on coming, at some point it is turned on, or at some point the device is created. So only then the periodic signal starts, right? So all practical signals are aperiodic. So now so how did we come to the Fourier transform? So we took a periodic signal with a period t, and then we studied its Fourier series representation as t tended to infinity. Okay, and we saw then in the previous lecture that this gave us led us to the Fourier transform. Okay, and so the benefit of having Fourier transform is that, okay, so the Fourier series is existing only for periodic signals. Fourier transform is existing for aperiodic signals, and then we can extend the Fourier transform so that it applies to periodic signals as well. So essentially, by using the Fourier transform, we can represent both periodic signals as well as aperiodic signals. Okay, so Fourier transform can be extended for both aperiodic as well as periodic signals. Okay, so this will give us a single unified framework for spectral analysis of signals. So we don't need to see that, okay, now we are given a signal, we have to first check if it is periodic. If it is periodic, then we apply Fourier series. If it is non-periodic, then we apply Fourier transform. We don't want that. We just want one thing to do both the types of signals. We just want one transform to handle both types of signals, both periodic as well as aperiodic signals. So that is why we can go in for the Fourier transform. So again we write it like this: x of t transforms to x of omega. It is also written as Fourier transform of x of t becomes x of omega, and the inverse Fourier transform is defined like this: f inverse of x of omega. Okay, and we saw the analysis and the synthesis formulas for the Fourier transform. There are a lot of properties of the Fourier transform. Since, of course, the Fourier transform is derived from the Fourier series, many properties are in common with the Fourier series. Okay, for example, I'll just list down a couple of them here. For example, if x of t is real, then the magnitude of the Fourier transform is even and the phase is odd. Okay, so this was the equivalent property which we saw in the Fourier series. Okay, in general, the Fourier series coefficients are complex, but if the signal is real, then the Fourier series will have the amplitude of the Fourier series will be even and the phase will be odd. So same thing happens for the Fourier transform as well. If x of t is real, the amplitude is even and the phase is odd for the Fourier transform. If x of t is real and even, then x of omega, that is the Fourier transform, is also real and even. Okay, so so the list of all the properties, please see table 4.1 in the textbook. So just one more word about the Fourier spectra, so that I want to drive home a particular point. Okay, so essentially the Fourier transform is to represent x of t in terms of everlasting sinusoids or exponentials. Okay, because we are using complex exponentials here. Okay, the important thing to remember is, if x of t is periodic, its spectra are at discrete locations. Okay, if the signal is periodic, its spectra are at discrete locations. And what are these locations? If omega naught is the fundamental frequency, it will be at omega naught and its harmonics, that is k omega naughts. So this is what we saw in the Fourier series. But an aperiodic signal has a continuous spectrum. Okay, here in the in the case of periodic spectra, we saw that the Fourier series is like this, discrete. It is discrete, right? This is omega naught, k, 1 omega naught, 2 omega naught, 3 omega naught, so on. These are discrete. But a aperiodic signal has a continuous spectrum. The spectrum is going to be continuous, like this. This is your omega axis. The spectrum in the omega axis is going to be a continuous function. Is actually a density function. The spectrum here is actually a density function. Density function is exactly same as the probability density function which you have seen in probability. Okay, so essentially, so if you consider your spectrum to be this continuous function x of omega here, this is your omega axis. So if you look at the contribution by any one exponent here, for example, at some omega, some particular omega, let's say omega dash, okay, you will see that that particular component gives you 0 contribution. So the actual measure makes sense if you consider only an infinitesimally small band of frequencies around omega, just like in the probability density function. At any one point of the random variable, I mean, what is the probability that the random variable takes one particular continuous random variable takes what is the probability that it takes a particular value? That probability is 0. Only around that value there is some probability value. Similarly, here in this case also, at a particular so it is around a small range of frequencies is the spectrum going to be of a significant value. Okay, so you can if suppose this the omega which you are looking at is k into delta omega, where delta omega is the width of the band. Okay, then what will be the area of the band? The area of this band will be 1 by 2 pi x k delta omega del omega. So this comes from the derivation of how we came to the Fourier transform from the Fourier series. Okay, so if you refer back to that section in the textbook where they derive the values of how the Fourier transform values are related to the Fourier series values. How are the Fourier transform values related to the Fourier series values? This expression comes from that. And this actually leads to the Fourier synthesis formula which we have seen here. This is essentially, so if you see this is how we are representing x of t in terms of complex exponentials. Only difference with the Fourier series was that in the Fourier series these were discrete. It was k omega naught for various values of k. But here in this case it is a continuous omega. Okay, but now you can directly relate this to this. Essentially what is happening is, if you see this, if you want to see this x of t as in terms of its Fourier series, what will be its Fourier series coefficients? Its Fourier series coefficients will be x of omega d omega 1 by 2 pi, and that is essentially what you have here. Here we are looking at, when you divide them into discrete units like this, consider this function to be divided into small units, and as this del omega becomes smaller and smaller. Okay, so in that case your delta, so the area here is going to be this shaded portion, right? So this is del omega and multiplied by the height of this rectangle, and that height of this rectangle is given by 1 by 2 pi x k del of omega. And so when you compare this with this, in the limiting sense, as del omega tends to 0, your del omega becomes d omega, your discrete k delta omega becomes continuous omega, and this is your 1 by 2 pi, and this is your 1 by 2 pi. So the Fourier series coefficients here will be similar to this. Okay, so this is how the synthesis formula of the Fourier transform comes from this. And the interesting thing is that even if you have finite bounded signals. It starts from some time A and finishes at some time B. Essentially, when we are synthesizing or when we are doing the inverse Fourier transform, okay, we are essentially representing your finite bounded signals in terms of everlasting exponentials. So a finite signal which exists for a finite amount of time is being represented by everlasting signals from minus infinity to plus infinity. The signals which last from minus infinity to plus infinity, which are essentially your complex exponentials, they combine in such a way to give you a finite length signal. That is the amazing part. Okay, a linear combination of infinitely long signals is giving you a signal of finite length. So now we will see how the Fourier transform is extended to periodic signals, because what we defined earlier was for aperiodic signals. Okay, so periodic signals which exist from minus infinity to plus infinity are neither absolutely summable or square integrable over minus infinity to plus infinity. So come back to the Dirichlet conditions. Remember the Dirichlet condition. The first Dirichlet condition was it should be absolutely integrable. One of the conditions for a signal x of t to have a Fourier transform or to have a Fourier series, the same thing for Fourier transform also, it should be absolutely integrable. X of t dt infinity minus infinity to infinity should be less than infinity. So if that condition is not felt, then the signal will not have a Fourier transform. But the Dirichlet conditions are sufficient conditions. So there could be signals which do not satisfy the condition and still have a Fourier transform. So that is what we are going to see here. Okay, we can still define the Fourier transform. So to get an idea of how we are doing this, consider the signal whose Fourier transform is 2 pi del of omega minus omega naught. Essentially, it is a scaled impulse located at omega naught. Okay, this is a delta function and it is a scaled impulse having an area 2 pi at location omega naught. Here we are looking at the omega axis. So this is an impulse in omega located at omega naught. So how do you find the x of t for this signal which has this other Fourier transform? You apply the inverse Fourier transform, and if you apply the synthesis formula here, and if you work this out, you will just get e raised to j omega naught t. Essentially, this signal has a Fourier transform equal to this. Okay, the Fourier transform of this is this. So what does this mean? So if you extend this and a linear combination, so each signal which we saw was of the form 2 pi del of omega minus omega naught. Now if you take a linear combination of them, you have 2 pi ak del of omega minus k omega naught, okay, for various values of k. So all of them, so essentially what this means is these are all shifted impulses at locations k omega naught, and the coefficients of the combination are ak multiplied by 2 pi. So going by the same example, what will be the equivalent signal which will have this as a Fourier transform? If this one is the Fourier transform of this, what will be the signal which has this as a Fourier transform? Okay, then we can get the time domain signal x of t by applying inverse Fourier transform and by applying the linear combination. You will see that x of t is nothing but ak e raised to j k omega naught t, right? Because each of them will contribute to a e raised to j k omega naught t. So x of t is nothing but this, and this is nothing but the Fourier series representation of xt. This is same as the Fourier series representation of xt. Essentially what this means is the Fourier transform of a periodic signal with Fourier series coefficients ak can be interpreted as a train of impulses occurring at harmonically related frequencies, for which the area of the impulse at the kth harmonic is k omega naught area is equal to 2 pi times the value of the Fourier series coefficient. So essentially, the area of the impulse occurring at omega naught is 2 pi into ak, where ak are the Fourier series coefficients of the signal. Okay, so we are looking at periodic signals here. We are extending the Fourier transform to periodic signals. So periodic signals will have a Fourier series. So how can you relate the Fourier transform of these signals to its Fourier series? It is given by this expression, or these two relations explain that. And the Fourier transform consists of impulses, and the area of the impulse is 2 pi times the value of the Fourier series of that particular periodic signal. For example, if you consider the periodic square wave, which we saw earlier in the Fourier series chapter, it had a Fourier series like this. This was for the case when this t was 1/4 this period. Okay, so we saw that this was the expression. This is the figure from the book. This was how the Fourier series coefficients looked like. So now how will the Fourier transform of the signal look like? By going by this relation, going by this relation, what we do is you take the Fourier series coefficients and replace all the Fourier series coefficients by impulses and scale the impulse by 2 pi. Okay, so the various AKs are like this. For A0 equal to half, and for AK is equal to sine pi k by 2 by k pi. This was how we had obtained the expression for each of the non-zero. These are the expression for the Fourier series coefficients where k is not equal to 0. So you take each of these values and multiply by 2 pi. Okay, that will give you the Fourier transform representation. So it is essentially the same. It's just that the Fourier series values are replaced by impulses here. Another example 4.7 from the textbook. X of t is equal to sine omega naught t. So this is a periodic function. The Fourier series coefficients we had seen earlier for this function are a1 and a minus 1. They are the only non-zero Fourier series coefficients, and this had the value 1 by 2j. This is minus 1 by 2j. It's an odd function, so these are antisymmetric. So if you multiply that by 2 pi, scale each of these values by 2 pi, you get minus pi by j and plus pi by j. So this forms the Fourier transform of sine omega naught t. Similarly for cos, okay, you multiply the Fourier series coefficients by 2 pi and you get two impulses at minus omega naught and plus omega naught. This is the Fourier transform. So in the Fourier series chapter, there was something about the impulse train. An impulse train is essentially a train of impulse functions like this, which are periodic. So here there is an impulse at 0, there is one at t, 2t, and so on. Each of these impulses have unit area. So this is an impulse train. It has the expression like this: del of t minus kt, where k goes from minus infinity to infinity. T is the period of the impulse train. So when so this will have a Fourier series, and if you see example 3.8, the Fourier series coefficients ak are all 1 by t for all k. For all values of k, all the Fourier series coefficients are the same, and that is equal to 1 by t. And essentially now the Fourier transform is now going to be multiplied by 2 pi, which is nothing but 2 pi by t. You multiply this by 2 pi by t, and we are replacing the location of each Fourier series coefficient is replaced by an impulse at that location, and that location is omega k minus omega naught, which this is equal to 2 pi by t. Right? Because these are located, the Fourier series coefficients are located at the various harmonics of the fundamental, like k omega naught. So this is how the Fourier series gets extended to the Fourier transform, and hence we can define Fourier transform for periodic signals. So please go through, more examples are there in the book. You can have a look at it in the textbook.